and move to the slides. Okay, so last class, oh, by the way, I'm going to try and go a little bit faster this lecture, but hopefully because we spent so much time on the fundamentals, it's going to be easy to follow because now you understand the basics, right? It should be no problem following me along, even if I do up the pace just a little bit. Okay, so last class we talked about interest formulas for single cash flows. So let me switch to a laser here, right? And so we said these are single payments that we're going to move either to the future or that we're going to bring back to the present, right? And we saw two factors. The first is this one that you see here, the compound amount factor. And this factor is what you multiply your present value with in order to compute the future value, right? So this is F computing future value given P at a given interest rate and for a number of years, right? And so this is called the compound amount factor. Sometimes it's called the growth factor. And we already know what this formula is. If I switch to a pen, it is this right here, right? That's the formula. And this in particular, this part here is the factor. You multiply P by this factor, by this multiplier. And we said you can find these in tables, or of course you can use the formula to compute them. And we saw some examples, right? And we also saw the opposite, which is called the present worth factor. So this again is a single payment factor. Sometimes it's called the discount factor, but this is P given F. So you're given F and you want to find P. So this is the factor, which is exactly this right here. 1 plus I, and then the exponent is negative. So this is moving right to left, present given future. And we started, we saw some examples. We saw one quick example where you just apply the formula, right? We already know in order to compute P, you just apply the formula. We're given F, we're given I, we're given N. So everything is just straightforward. And we found this answer. And then we started, I think this is where we stopped. We just introduced this example. I think, if not, then I'll just go over it very quickly. I'm not going to spend too much time on the examples for the single payments because, I mean, we have other things to get to. So in this example, you're actually given P and F. You're given the present value and future value, and you're given a time horizon of 5 years. And the question is to find I, what is the interest rate that sort of satisfies these three requirements, right? In other words, what is the interest rate I, at which if you invest P, which is $10 today, you will get $20 after 5 years, right? That's another way of like asking the question. And sometimes the interest rate is just going to be called the rate of return. So we're going to see this more and more often as the course goes along. So just know that, right? So I can be interest rate, can be discount rate, also can be rate of return. And so this is what the cash flow diagram looks like for this example, right? So you're investing $10 today and then getting back $20 in the future, 5 years from now, and it's asking you to find I. And we've seen how we can do this, so I'm just going to go over it very quickly. We have 3 of the 4 sort of parameters in the formula or variables, and so you just have to solve for I, right? And how do we do that? Well, we can just manipulate this expression either by taking logs or by raising things to the power, let's say 1/5. So this is if you want to do this analytically. You could also, of course, use the tables. And hopefully it's easy to see that because you're solving for I, and if you remember, we said we have a table for each interest rate. So you're going to have to look through multiple tables until you find the factor. So you see here from this expression, after you plug in and sort of manipulate things, you get that this factor, which we know is the compound amount factor, or yes, this is the compound amount factor, right? Because the exponent is positive. And so this factor is equal to 2. So what you're going to have to do is you're going to look through interest tables one by one. Look, here it says here, you're supposed to look at the row corresponding to n equals 5 and look under this column. And look from table to table until you find 2. So you have to find the compound amount factor that is equal to 2 in some interest table I. And once you find that, that's going to be, you look at what the value of I is for that table, and that's going to be your I. And that solves the problem. Or you can just do this using math, right? Which I've just explained. You can raise these 2 sides to the power 1/5, which is exactly what they do here. You can also use logs or lins, as we've seen before. All of them should give you roughly the same answer. I'm actually not sure if the book like has tables for 14.87%. Probably not. You may have to see tables for 15%, for example. And so you get an approximate solution. So in that case, it's just better to use algebra to find the answer. Okay. And so you can also be asked to solve for n, right? Again, you're given three of the four variables, and you're missing just one of them. So a question would look like maybe, how many years would it take your investment of $3,000 to double? So you get $6,000 back if the interest rate is 12%, right? And you're supposed to find n. How long, right? That's n, right? That's the horizon. How long will it take my money to double? And I can do pretty much the same thing, right? Hopefully it's easy for you to see that if I just plug in, I have an equation and I need to solve for n. Now, of course, n is in the exponent, so one nice and easy way to deal with it is to use logs, right? To bring this n down so that I can bring it down here somewhere. Of course, maybe I would divide first by 3,000 on both sides to get rid of this here, and then I will take logs. And if you do that, so I'll leave this for you to follow. You can just compute it, and you find that it's 6.12 years, right? So again, I mean, once you substitute in the formula, it's just algebra all the way through. Or you can also use tables, again, in a similar way, but in this case, you would actually look for the row, right? N is rows, so you would look for the row that gives you the value that you want. But I would rather just use math, right? A nice little thing to know is that if you look at the statement of this problem here, it says, how long will my investment take to double, right? So there's this nice little rule called the rule of 72, which approximates how long it will take for any sum of money or any investment to double in size. And what this rule says is that if you want to find how long it will take, so you want to find n, you take 72, that's where the name comes from, the rule of 72, and you divide by the interest rate of the problem. So in this problem, we saw that the interest rate is 12%. So I take 72, I divide by 12, I get 6 years. If you look at the actual solution, it's 6.12 after rounding. And so our solution using the rule of 72 is a pretty nice approximation. So if you just want to quickly compute how long it will take for your investment to double in size, just 72 divided by whatever interest rate, and it will give you an approximate value for the number of years it will take. Okay, here's another problem. I'll go through this maybe in just a little bit more detail because maybe like this is a new twist. Also, you'll see a problem like this in the homework. And so here you're given an interest rate of I equals 10%. And you're given two different cash flows. At least they look very different, right? One has $500 today, $1,000 3 years from now. The other one has two unknown payments at years 1 and 2, both with value C. And it's asking you the following. It's asking you find the value of C that makes these two cash flows, even though they look different, I want to make them equivalent. And so you see here economic equivalence again, right? We've already seen that sometimes cash flows might look different, but I can make them equivalent, or maybe the right interest rate makes them equivalent. And so here you're actually given the interest rate, but the payments are what's missing. And so can I solve this problem? Can I find a way to make these two cash flows equivalent and then solve for C? And the answer, of course, is yes. And so I want you guys to tell me how I can do that. Mazen, go ahead.
Yes, in the first cash flow, we can move the 500 to year 3, and we find the equivalent. And we can compare it with B while we move C, both C, to year 3, and we equate them.
Exactly. So that is 100% correct, what you said. So what Mazen said is we move the 500 to the future, right? Again, we use the formula. We just plug in. We find F given P for the 500, and we add it to the 1,000, right? So this is a time period 3. That's our base time period, if you remember. And we can do the same thing here. We use the same base time period, and we move these here. The only difference is what we're going to get here is something in terms of C, right? It's some expression, I'll write just F of C, some expression in terms of C. And then we equate the two. So we equate the value that we get here after moving the 500 to F of C, and we solve for C, right? So hopefully that's kind of straightforward. And we'll see here in this example, I think they actually choose a different base time period. Again, that's completely fine, right? You should get the same answer. And so here the base time period that they choose is 2. You can use 3, you can use 2, you can use 1, you can use 0, just pick whatever one you like. And so here, so that's the base time period. They're going to find the equivalent sum for both A and B by moving. So here they move this one here with a positive exponent. Here they're going to move the 3 back with a negative exponent, and here they're just going to move the c with a positive exponent. I think there's a question. Mohammed, yes?
Yes, Doctor. I think you said that it is we should choose the one that makes the calculation easier. So isn't it two will be better to choose two?
No, I mean, they're going to be the same, right? Because here you're moving 1. So if you choose 3, you're moving 1 in A, and you're moving 2 payments in B. If you're choosing time period 2, then you're moving 2 payments in A and 1 in B. So it's the same. You're going to do 3 sets of calculations in both cases.
Oh, okay. Thank you.
Yeah. So you're absolutely right. You choose the one that makes like that is easiest for you. In this case, you're going to do 3 calculations in whatever case you choose, right? Because all of them, because you have a payment, you have a single payment at each time period. If you look, 0 has 1, 1 has 1, 2 has 1, 3 has 1. So you're going to have to move 3 payments anyway. So in this case, it doesn't really matter which one you choose. If you choose 1, you're going to do the same number of calculations as well. It doesn't matter. But you're right. In general, I mean, if you did have, like if you had 2 payments, let's say, at time period 1, 1 in A and 1 in B, then it would make sense for you to use that instead, because I mean that means you have to do less work basically. Okay. And then yeah, like Mazen I think said, you equate both values and then you solve for C, right? And so this is what it looks like. Just going over it quickly. So here again, they're moving the 500 2 time periods in the future. They're moving the 1,000 1 time period sort of backwards. They're going to get value. And then for B, they're doing the same thing, except that the value that they get is now in terms of C. And now I could just put the 2 equal, remember, because of equivalence. I want them to be equivalent. And then I solve for C, and I get $721. So if these 2 C's were 721, these 2 cash flows are equivalent. I'm indifferent between the 2 because of interest. And if I manipulate the numbers, like if I move this here, I will get this exact same cash flow. So they look kind of different, but if C was 721, the 2 are really the same cash flows. So here's another practice problem. I'm not going to go over this in detail because it's very similar. Now it's giving you a cash flow, but it's asking for I. Right? So it's a little bit different, but it's sort of the same thing. How can you make 2 different cash flows equivalent? Same principle. And so we do pretty much the same thing, right? And so you're going to pick a base time period. So here, notice that we picked 3, because 3 is common to both of them. So I can manage to like get by with less work, because if I move this forward and then I move these 2, that means I only have to do 3 movements. Whereas if I picked, let's say 2, I'll have to move 2 here, and I'll have to move 2 here as well. So I'm doing 4 sets of calculations. So because the 3 is common, I'll just choose 3, and then I'll move the payments as necessary. Right, and we do the same thing, right? We apply the formula. So this is what we get for option A and for option B as well. Now, in order to solve for I here, it may get a little bit tricky because, I mean, you have cubes, you have squares, and it's a little bit messy if you want to do this algebraically, and you may not even be able to, or at least, well, you have 2 options. Maybe like one easy option is to use some sort of numerical optimization software that will find or search for I that makes these 2 expressions equivalent, right? So this is what we want. We want these 2 to be set equal to each other, right? Because this is F here, FA, let's say, and this is FB. I mean, they're using 3 and 3. I would have used A and B instead, maybe. But we want them to be equivalent. So you could just plug this into a software. You can actually use Excel also for this. There's a function that's called goal-seek, which I encourage you to search for. It's very easy to use, and it will be useful in your homework if you don't want to do things by hand. So it will do this for you. It will try to search for I that makes the 2 expressions equivalent. Otherwise, you can just use trial and error if you don't have access to like software. And so you can just plug in. And in this case, they plugged in 8%, right? If you plug in 8%, you actually get that both are equal to each other, right? 1630 for option A and 1630 for option B. And so then you find the solution and you say that's it. The I, the interest rate that makes the 2 equivalent, is 8%, or approximately 8%. I'm not sure if these are exact. I imagine they are, but just in case they're not, you can say that it's approximately 8%. Okay, so here is another example, just fairly quickly. So let's say you're interested in buying a house, a piece of real estate, right? Aqar. And you know it's going to be worth $200,000 in 5 years. So this is kind of your F, right? This is what it's going to be worth after 5 years, $200,000. Assuming that the interest rate is that the interest rate is 9%, which is I, right? So this is your I. How much would you be willing to buy it for today, right? So I mean, it's kind of saying today here in brackets. So you know how much it's going to be worth in the future. How much would you be willing to pay for it today? And so what we need to do, again, we're given sort of N here, and we're given F, and we're given I. So you need to solve for P. And so what is P here in this case? It is the present worth. It is how much this house that I believe will be worth $200,000 in 5 years, how much it is worth today. And I find this number. Based on this number, when would I be interested in buying the house? Well, I know that this is how much I think the house is worth today. So if someone asks me to pay less than this amount, then it's a good deal, right? Because it's worth $130,000, but I'm paying less for it, so I'm getting a good deal, right? So that's when you would be interested in buying this house, because it is less. You're going to pay less than you think it's worth for it. If you're going to pay more, then you're going to say no, because I think it's worth a lot less than what I'm paying for. And so this is like another, I mean, the equation and the calculations here are kind of the same. It's just maybe the new twist, like, of answering a question about like when you would be interested in buying this item based on its present worth. Okay. And so that concludes. So again, like I said, there are other practice problems that I skipped over that are not shown here. They are in the version that I just uploaded in the slides. So please go over them, make sure you understand what's going on there. And they're very simple. I just didn't want to waste too much time on them. So now we'll turn to what the book calls an uneven payment series. I'm not sure why they separate this into its own category. So remember, what we saw before was single payment series, right? And so we saw that that's moving a single arrow or a single payment from the future to the present, and from the present to the future. Here they're talking about uneven payment series, which means it's a payment series, so it's a cash flow that may be just uneven, meaning like you have payments like this, a payment like this, I don't know, a payment like this. So it's not, we're going to contrast this later with even payment series, right? So an even payment series looks exactly like this. For example, I mean, it's just a bunch of, these all should be like the same height, but my drawing capabilities are unfortunately not great. So these should be the same height. So equal payment series or even payment series look like this, right? All the arrows are the same height, except maybe the first one where which is the investment arrow, let's say. Whereas uneven means all these arrows are like very different. So I'll just draw like here. You see they go up and down, up and down. So they are very uneven. So I'm not sure why they do it, like why they split it off its own category, because it's kind of exactly what we covered before. It looks exactly like a single payment case, except you're going to have to move each payment individually, which we've already been doing in a way. So I'm not really sure why they call it, why it's its own section or subsection, but it is what it is. So in this example, let me see what's happening. So or let us all see what's happening. So as you know, in the US and in other countries, going to school, so going to university, costs money. And so you have to pay tuition, and you also have to pay fees. And so here what they're saying is that suppose you join in the year 2008, right? So that's your first year at the school. They give you the option between paying each year in its year. So you pay your tuition on a yearly basis. So first year, you're going to pay this amount, $32,882. The next year, they're going to tell you that the payment increases, but they don't tell you exactly how much it's going to be. You don't know that. But they say, I mean, likely because of interest, we're going to increase the payment, right? And similarly, the year after that and the year after that. And college in this scenario lasts for 4 years, right? So if you join in 2008, you're going to pay this amount in year 1 or year 0, I guess, depending on how you count it. Then this amount in year 1, this amount in year 2, and this amount in year 3, right? So if you start from 0, that's 4 years. But you don't know it in advance when you were given the option, right? You don't know these 3 values. So these are question marks. This table is from the perspective of someone who just graduated, for example, in the year 2013, and they're looking back. Now they know all of the values, right? But when you join, you don't know that. The other option they might give you is to pay one lump sum. So they say, you can also pay this amount right now. And of course, your question is, which one is better? Do I pay on a yearly basis, or do I pay this lump sum? And so they're asking this question again from the perspective of someone who just graduated, and they're looking back. So it says looking back 4 years from the time of enrollment, which I think in this example is 2008, right? It's 2008, 2009. So now that you know the values, which one was a better decision to make back in 2008? Like with hindsight, which one should I have made, right? And you can, they're giving you that the interest rate is 6%. And so in fact, in this example, I think they say that the student chose the prepayment, so they paid the lump sum. And so they're asking whether or not that was a good decision. And so what we need to do is basically the same sort of thing we've been doing up until this point, which is we need to find the present worth of all of this sequence of payment, right, this series, at time 0. And then we can just compare it directly with this number, right? So once we move this back here, sorry, this is getting a little bit messy. So we move these payments to time 0 with the interest rate of 6%. And then we directly compare to this value, and then we see which one was the better decision, which one was cheaper. Okay? Uneven, because the payments are not equal over time, right? That's why it's called uneven. And here we see that at time 0, so these are the numbers that we see when you join in the year 2008. So you remember this number was the first one, and then they increase a little bit for 4 years. What are we going to do? Well, notice, first of all, that the first payment, you're going to make it now. So that one I don't need to do anything with. That's already in today's dollars, right? And that's how much this payment is going to be worth today. It's already, it's ready for me. I need to move these other ones. So I need to move this 1 back, this 2 payment back, and this 3 payment back. And then I need to add all of them together, right? So that's what they do here. They move P2 back, move, sorry, P1, move P2, and then, yeah, well, they're using different, okay, they're using weird notation, but in any case, you just do exactly what I described here, and then you add them all together, and you find this value here. Now, what do? We just compare this value to the 131,000, and of course, we notice that paying on a yearly basis, which is this cash flow here, is cheaper than the prepayment, which was 130 something, right? And so, in hindsight, the student should have chosen to pay tuition on a yearly basis instead of paying one lump sum. And so again, you see here sort of the question of alternatives. You have a decision problem between 2 different alternatives, and we now have a way to compare things together. So using the interest rate, I can just pick a base time period. In this case, that one, that base time period was 0. Move everything to 0, and then make a direct comparison between the 2 alternatives. So that's exactly what's written here. Question, Mazen, yes?
Yes, doctor. In the previous slide,
Yes.
we were talking about 2 options the students should pay. So why in the cash flow we have 2 directions? The arrows have 2 directions.
So that is a good question. I kind of had the same question actually, looking at this. But if you remember what I said before, let me erase the pen. So I think what's happening in the book is the following. They're framing this question as like an investment. So they're asking like, what is the equivalent? So what is the present worth? What is P for a series of incomes that I'm getting? So it's just the framing, and that's why they're reversing the arrows. However, you can just as well do exactly what you were describing. So if it's a payment, just put the arrows down, which makes a lot more sense to me and hopefully to all of you as well, because you're paying these over years and it's not income. It's just the way that they framed, the way that they were going to solve the problem in the book. They framed it as an investment, if I remember correctly, and that's why. So that's why the arrows are going up, and that's why you have this here. So it's basically they're saying if you receive this income over 4 years and then you want to know how much that income is worth today, this is what the cash flow would look like. But you can convert this, of course, into arrows that are down, and then the present worth can also be down, because you're finding the equivalent of a bunch of payments that you're going to have to pay at time 0. So the answer should be the same. The calculations are not going to change, right? The numbers are still going to be multiplied by the same factors, so that's the good thing. It's just, like I said before, just make sure to be clear on what you're doing. So if you want to adopt the convention in the problem that is that these are payments, you can use this approach. That's completely fine. I think it's more clear. I would go for this approach. However, in the book, because they start by asking the question a little bit differently, so they say, what is the equivalent, or so they say that this problem is equivalent to asking what is the value of P that would make you indifferent between receiving P dollars today and this future income, which looks like this. So they framed it differently. They framed it as income, and then they solved for it that way, and that's why it looks a little bit different. But the answer should be the same. The numbers should be the same, so no worries there. As long as you're consistent and you're clear on what you're doing, it should be fine. Okay, and we already saw this. This is what we get basically. We get this value, which is less than the prepayment option. And so as we said, so this is prepayment, the lump sum, and this is on a yearly basis. And so this option here is going to be cheaper. So in hindsight, the student should have opted for paying tuition on a yearly basis. Okay, now we're going to turn to the main topic of today. I think we're actually doing good now in terms of like being on schedule, because I imagine I would finish the rest of these slides that I wanted to finish today, hopefully, but I'll try not to slack off and run the risk of not doing so. So I'll try to, if we finish early, good. If we don't, then I want to make sure at least like we get through all the slides that I wanted to get through today. So now we switch from single payment series and uneven payment series, which again, I don't think it should be its own category, to equal payment series. Why are we going to do this? Well, for equal payment series, even if you had a cash flow that looked like this, for example, right? You had equal payments every year. Again, these should be roughly equal. I should have drawn the line first maybe, and then drawn the arrows. Even if you had a cash flow that looks like this, you can do the same thing that we've been doing so far, right? You can, if you want to find the present worth, just move these arrows one by one. However, because these are equal payments, we're going to find a nice little formula that allows us to get a shortcut, basically. So instead of moving these payments one by one, you can do the entire calculation and find P. If you wanted P, let's say, given the amount of these equal payments, you can find that in one go. You can just plug in the formula, it will give you the answer. So the reason why we're doing this separately is because it's kind of a special case and we have a nice formula for it. And that allows us to save a lot of time instead of doing them one by one. And we're going to look at a bunch of factors. So first of all, just notation. Let me redraw the cash flow diagram here so it's clearer. So I'll do the line first, which again is not very straight. So let's say these are the payments that I'm making. Right, and maybe this continues for a number of years n, and so here is the last one. So just a little bit of a notation. Each individual payment, if you remember from before I say that, if you remember from before, we had something called a sub n, and we said, for example, a1 is the payment that you pay at time period 1. And so in this case, because they're all equal, so we have that a1, so this is 1, right, 2, and we start at 0. A1 is equal to A2 is equal to all of them, well, equal to all the way up to AN. And we're just going to call each individual payment A, right? So you already kind of see A here. That's what A is. So A is the individual payment that you're making at a particular year. And it's going to be the same for all years because it's an equal payment series. Okay? Now you notice, well, you can find the future value if you wanted to, right? So that's here. And you can also find the present value if you wanted to, and that's here. So now we have this additional A, right, that we didn't have before. So we have P, we have F, we have I, we have N as before, but we also have A. And so that's why we have a few more possibilities for these factors, right, which, and the factors, remember, they tell us sort of how to compute the multiplier to find what we want to find. So the compound amount factor for equal payment series is actually similar, at least like in terms of notation or in terms of like what it's referring to. It's actually very similar to the compound amount factor for a single payment series. And if you remember, for a single payment series, the compound amount factor is the future value because it is what is the amount is after compounding interest for a number of time periods. So that's how you should remember this, right? And so in the single payment case, it was F given P, right? Here, however, because it's an equal payment series, we're going to use A to find the future value, right? So you're paying a bunch of payments over a number of years, and then you want to find the future value that you have paid over those years. And so in this case, it's going to be finding F given A, and of course I and N. Now, of course, we can also do the opposite, right? You may be given a future value for an equal payment series, and you need to find these individual payments. And so that's just the opposite. So that's finding A given F. And that is called a sinking fund factor, and we'll see why. And then, of course, you can find P. So we have two factors here that are related to P. And they're basically kind of the same thing. You may be given A, and you need to find the present value. So that's called the capital recovery factor. And then you may be given P and asked to find A, and that's called the present worth factor. And we'll see detailed examples of all of these, by the way. So don't worry about not absorbing anything on this slide. I just wanted to introduce to sort of give you the lay of the land, and so you can see where we're headed. Finally, you may notice that this may look like a typo because it's exactly the same thing as this one here. However, the word perpetuity means something that is going on indefinitely, so something that is going on for infinity, right? And so these are payments, we'll see them later, where you're receiving the same amount every year for an infinite number of years, right? So N here goes to infinity. So this is kind of a special case by itself, whereas these four, every pair of them are related, right? But here, this is a case where N goes to infinity, and that's why, even though it's not indicated here, but it looks exactly like this because because of I will say something. So of course you may be asking, why don't I have an F, let's say, given A for this case, right? As N goes to infinity, and we'll see why. We'll see that even though the payment, you're getting an infinite number of payments, right? So the sum, you think it's infinite, right? Because each time you're getting the same amount for every year. Actually, you can't compute the future value because N goes to infinity, but it has a well-defined and finite present value because of math, basically. We'll see that in a little bit, so don't worry about it. So these are all the 5 different factors for equal payment series, and we're going to go over them one by one. So before we do that, here's again a much better drawing of what an equal payment series looks like, right? So you start at the first payment. The convention is going to be, in all of the formulas that we're going to use, assume the following. The convention is going to be that we start a payment from time period 1, especially if you're computing the present value, right? So if you want the present value, always remember that the present value that you're computing should be, or is going to be, one time period before the first payment. So this is important, and we'll see examples of this, like what happens if the first payment starts at 0. Then I'll have to do some manipulation in order to work things out, okay? And also, you have N payments, right? You see here, N payments from 1 through N. And the future value is going to be calculated at the last one of these, exactly at N, okay? And so again, you can see here, you can find the future value all the way at the end, or you can find the present value. I mean, see here, I drew the arrow down. Here it's kind of up. Sometimes it doesn't really matter, I would say, as long as the problem statement is clear. I mean, if this was an investment and you're getting back money over the course of the years, then what I drew here may be more accurate. But if it's not clear, if it's an investment and you just want to find the equivalent worth of all of these, right, at time period 0, then you can draw the arrow going up, right? Because it's still a payment. Sorry, it's still income, because in this case, all of these guys are income. So it really depends on the context of the problem, which way you draw the arrows. Okay, so now we're going to start with the first one. So the first one is the compound amount factor. And so this one, as we said before, is you're going to find the future value given A. Okay, and same as before, we're given an interest rate and a number of years. What does this look like? So again, the first payment starts from 1, and here we're actually paying money for N years. and we want to find the future value of those payments. And so again, the direction of the arrows depends. Like you can think about this as depositing money into account, so you deposit the same amount every year, and you want to find out how much you're going to be able to withdraw, so that's why the arrow goes up, at the end of the end time periods. Okay, so that's like an example of this scenario. And notice that the future value again is computed at time n. What is the formula for finding this? So again, I told you we're going to have nice and simple formulas. And so this is what it is. So this is the factor. This is the compound amount factor for the equal payment series, right? You multiply that by the value of A, which is the individual payment, and you get your F, right? So this is exactly the factor that I've written here. Now you may be asking, how do we come up with the formula? Well, you can actually do this yourself. And I mean, we'll go over it in the next slide, but I mean, you can see where it's coming from because it's basically applying the same thing that we've learned before. Just move all of these payments one by one to the future and see if you can find a nice little expression for it. Apparently we can, and that's why we have this expression here. Right, and so this is the compound amount factor for an equal payment series. Okay, and so here's the derivation. Hopefully this looks very obvious and familiar to all of you, right? So we're taking each payment and we're moving it. So this is moving the payment to time period 1. We're moving it n-1 time periods forward. Similarly, the one after that, it's n-2, all the way to the last one, which is actually at n, right? So this here is at n, the final one. So that's why we don't do anything with it, because it's already at the future value point. Now, of course, I can take A as a common factor, right? So I'll write it first and then I'll just erase it, right? So if I take A as a common factor, I will have 1 plus I to the n-1 plus 1 plus I to the n-2 plus all the way to plus 1 at the very end, right? So hopefully everybody sees that. And I can write this, I'll just continue writing and then I'll show you what the slide says. I can also write this as follows, right? So the A stays the same. This here is a series, it's a sum, right? And I can write it more compactly using summation notation, right? So I'll start from something, I'll end at something, and then I want to sum something that looks like 1 plus I, hopefully to the power k. And so if you notice here, I'm starting from 1. So in order to get this to be 1, I need k to be 0 at first, because anything to the power 0 is 1. Right, so if I start from 0, and then I keep going, of course, until n-1, right? This is exactly equivalent to this. Does anybody know what this series is called? Or what it looks like? Any guesses? Mazen?
I think it's exponential sum.
I'm not sure if exponential sum is the same thing as what I'm about to say. Yes, there's a specific name for it. I mean, these are not the names I know. You guys may be saying like the correct names. I'm just not sure like if they're synonyms for the same thing. But this is I'll just write the name here. So this is known as a geometric series. However, there's a little bit of a twist. So sometimes we call these partial geometric series. I'm not sure if that's actually a standard name. It's what I use. I say it's a partial geometric series because a geometric series looks like this, but the only difference is that you're summing all the way to infinity, right? So this is infinity. That's what a geometric series is. This is partial because you're stopping the sum somewhere. And so I don't know if they're also called power series, maybe. I'm not quite sure. But geometric series is the more common name, right? And so we know from math, and I'll just erase my pen here, and I'll show you so this is what I just wrote down. We know that if you have a partial geometric series, that this is the formula, right? So this is, again, something to the power of the index all the way to some value n. So it's a partial because we're stopping it before we get to infinity. This is what we should do. This is what the sum is, basically. And so in order to translate what I have here into something that looks like this, I need to find out what x is. So x, hopefully it's easy for you to see that x is equal to 1 minus I. 1 plus I. Right? And so then I can just substitute, right? So the formula says I need to do 1 plus I to the power of the final index plus 1. So here the final index is n minus 1. Plus 1 gives me n, right? So just write it down here. So 1 plus I to the power n. I'm just substituting here, right? Minus 1 divided by, and then I need to do x minus 1. But I know x, for my case, is 1 plus I minus 1, right? And so these ones cancel. And so I'm left with this, 1 plus I to the power n minus 1 over I, which is exactly what we found before. All right, so this is just the proof or the derivation for this formula. So here's an example of how to use this formula. So let's say you're investing your money in a savings account. Again, this is very common with investments, right? If you're investing the same amount every year, and you're going to withdraw your money at the end of 5 years. So it's saying here that in this case, I actually should have hidden the solution. Okay, never mind. So it's actually saying that you're investing $5,000 per year for 5 years. Your interest rate is 6%. And you're supposed to find F. Okay? What do? Well, we just plug in, because this is just a straightforward example. Everything looks in sort of standard form, right? The first payment starts at 1 and the future value is at 5, so we're good to go. And so we just plug in, and A is 5,000. This is the factor, right, which we can find using tables, or we can just compute using the formula that we just had on the previous slide. And if you compute it, again, using the table or just using the formula, for the factor, you're going to get this amount, right? This is just the 1 plus I to the n minus 1 over I. That's what the 5.6 is. And then you just multiply and you get the final answer of $28,185.46. Okay, so this is very straightforward. Here we're just saying that we can verify the solution actually by hand. How do we do that? Instead of using the formula, what you can do is just move the payments one by one, right? So these payments are always going to be the same, 5,000, and you just move them by the correct number of time periods, and then you add them up. Exactly the same thing that we've done before, and you get the same answer. So that's good. It tells us that we're doing the right thing. I mean, if the proof that I showed you before didn't convince you, or you didn't understand it, then hopefully this convinces you a little bit more that we're doing exactly the same thing as we did before, except now we have a nice convenient formula to use. And so here's what I was talking about before. What if there's a shift? And so notice here that the first deposit occurs at time period 0 instead of 1, and the future value that I need to find is at the end of time period 5. So the future value is not exactly coincident with the last payment. So this is not in the sort of standard form, if you will. So I need a way to handle this. And so what do you think I should do in this case? Any suggestions? Mazen?
Yes, we can do the compound amount factor up to year 4 or the 4th period, and then we can use the simple formula that we used in the other examples just to shift it to year 5.
Exactly. Right. So what Mazen said is 100% correct. That's at least one way you could do it. Of course, there may be other ways. But remember, if you compute f given a, so if you use this compound amount factor, it's going to give you a future value here, right? That is corresponding to the last payment in the series. With the future value, the first period doesn't really matter that much. It matters like where you're computing the future value, where you're computing the present value. For future value, even if the first one starts at 0, it's kind of fine. Just know that when you compute the future value, you're going to get a future value that is exactly corresponding to the last payment, right? So here n equals 4. That's where the future value is if you just plug in the formula. Of course, another way you can solve this problem is just to move the payments individually. But if you want to use the formula, right, you have an equal payment series, you want to use shortcuts, compute the future value at time period 4, but then I need the future value at time period 5. Well, now what I have here at time period 4 is just a single payment. And I can take this sum and just move it forward by one time period using the single payment compound amount factor, the simple formula, like Mazen said. So the f is equal to p1 plus I to the n, where n in this case is just going to be 1, right? So n is equal to 1. Sorry, here I'm right? So again, 2 steps. You first compute the equivalent worth of the equal payment series at time period 4. That's exactly using the formula that we just went over. And then you just move it 1 time period ahead in the future by applying 1 interest factor to it. And that gives you the future value at time period 5. And so that's what the slide says. So again here, you see why we use this notation, because it's kind of convenient and I don't have to write complicated formulas. If I just say this, you know what to substitute here, or you can use a table, right? And so here you take a 5,000, you apply the compound amount factor for the equal payment series, right? 6%. You have 5 payments, 1, 2, 3, 4, 5, and so that's why this number here is 5. And then you take that sum, whatever it is, and you apply 1 plus 0.06 to the power 1 to it, because you're moving it 1 time period at the end. And you get this answer. And I encourage you to verify this solution by checking what happens if you move each individual payment 1 by 1. You should get the same answer. All right, so this is how we can handle these time shifts where things are not quite in standard form when we're computing the future value, or sometimes when we're computing the present value. You have to manipulate things to get what you want. Okay, so now here's the second factor, which is the opposite of what we just described. So suppose that you're given f, you're given what the future amount is, and you want to find what is a. You want to find the equal payments that you should make in order to have a future value of f, whatever f is, right? And so this is called a sinking fund, or a sinking fund factor. Why is it called sinking fund? You can think about it like if you want to have X amount or F amount of money after you retire, for example, or in order to save for college, like if you live in a country where you have to pay for college, and you want to know how much you should set aside each year in order to have that future worth at the end of n years. This is exactly what the sinking fund is. So you're sinking your money into a fund, right, into an account. And so that's why it's called sinking fund. You need to find how much to sink or how much to pay each year. Okay, so this is kind of what we had before. Any guesses for what, like, how to do this? You should already know how to do this based on what I just told you. What does the formula look like?
The power may be negative because we're computing something in the past.
Roughly speaking, yes. But so if I show you this here, can someone tell me what the formula looks like? So let me erase the pen. So remember, right? So this was for f given a. What I want now is a given f. What should I do? Of course, Mazen knows. Maybe just give the other students a chance now. Oh, there's one more. So I'm going to lower your hand, Mazen. Just give me a second. Oh, Khalid. Yeah, Khalid, go ahead.
Just divide the factor, the f over the factor to get a.
Exactly. Right. So hopefully it's easy for all of you to see that if I just divide by this on both sides, right, or I just move this here, I will have to flip it. That's my formula, right? So that's a as a function of f, a given f. Okay, and so I'll show you that actually here on the slide, but I mean, we're not saying anything new here, is my point. Here it is, right? So a given f, it's just the reciprocal of that factor. So it's kind of what you said, Khalid, in the beginning when you said it's a negative exponent. I just wanted like to be a little bit more concrete, but you're absolutely right. It's almost the same thing, but with a negative exponent. But the thing that you're sort of flipping is, or you're putting a negative exponent on, is this factor here, the total thing, not just the 1 plus I, for example, as before. Okay. And so again, here's an example. You're saving for college, and you know how much you need to save, or how much you should have at the end of the 8th year, at the end of 8 years, right? And you know the interest rate is 7%. And so the question is, if you start saving now, so you're saving when you're 10 years old, and you want to have enough money when you're 18, sorry. So 8 years from now, how much should you set aside each year in order to have this amount? And so this is just a straightforward application of this formula here, right? So we're given f, we're given I, we're given n, we want to find a. So n is 8 because we have 8 payments. Always make sure that n is the number of payments, right? Not sometimes, because things can be shifted. You don't want to make a mistake and look at the last one and say, for example, like we had here. Let me erase the pen so it's a little bit clearer to see. Don't just look at this and say I have 4 payments and put n equals 4, right? Because you have 5 payments here because we're starting from 0. So just be careful about that, okay? And so, yeah, we just plug in and we find the value. So if you set aside this amount every year, you're going to have enough money 8 years from now, okay? And so now we're going to switch to computing present values for equal payments here, right? And so the first thing that we're going to do here is something called the annuity factor or the capital recovery factor. I mean, these are just fancy names, but really what we're after is the following: is we want to find A if we're given some present worth or some present value P. So now we're shifting sort of towards the beginning of the equal payment series, whereas before we had F was at the end of the series. And so for P, in order for things to look in like standard form, we want the following. We want always that we compute the present value one time period before the first payment. At least if we use the formula directly, it's going to give us something that is one time period before the first payment. So just be aware of that. Here's what the formula looks like. So if you want to find A given P, this is what we should do, okay? And you may kind of already see where this is coming from. This part here looks very similar to what we've had before, right? What does this part remind you of? The remainder.
Compound interest.
Yes, what is like the variable for this part?
The F.
Exactly. So this here is F. So if you notice, like this is kind of the same formula that we had before. It's just because we need to find P, we're sort of extracting it from the formula that we had before. Like, I guess what I'm saying is that this isn't really anything new either. Like if you think about it, I can just find F for this payment. So let me go here, for example, in one of these, I can find F, which is here, and I can just move it back. That's another way to do it, right? And so that's kind of what this formula is. Like if you unpack this is kind of what you're doing. You're finding F based on the formula that we had before, and then you're moving it back all the way here to the beginning. Okay? So that's another way you can solve the problem, or you can just plug in if you have the formula ready for you. Yes, Salman?
Dr. Will you provide a formula sheet in the exam or quizzes?
So that's a good question. Because the exams are coordinated and this is my first time, I'm not sure. However, as always in these things, I will always advocate for a formula sheet. Like I will always insist on one. However, if they say that there is no form, I think what they do is they give you formula sheets instead of you writing your own. They will just hand out, because there is a page in the book that summarizes all of these formulas. So I imagine they would just give you that handout during the exam. So in that case, it should be fine. But in the event that they say no formula sheets are allowed, we're not going to give you anything, and we're not, you're not supposed to bring anything with you, I'll let you know in advance. And that's unfortunately, yeah, that will be very unfortunate. I'm not, like if it's something you could look up, you should always have it with you during the exam. So I don't want to waste like your brain space memorizing these formulas. And so hopefully, yes, there will be one. I just don't know for sure. Okay, so here's another example. No, actually, this is the same example, right? I think. Yeah. Oh, this is an example, right? We just started the thing. So here's a sequence of payments, right? A's for 5 years, and we want to find the present worth. Again, this is just straightforward. You just plug in the formula, right? So what we want to find is P. Actually, oh no, we want to find A. Sorry, yeah. So we want to find A given P, right? And I and N, of course. And I can just find the formula, which is exactly what we've seen here, and plug in, and I will get $5,000. That's how much I should set aside. So in this example, they're paying off a loan, right? So they're borrowing money for this amount at time period 0 right now. So this is P, and they want to know like how much they would have to pay each year for 5 years in order to repay that loan completely, with interest, of course. And so that's how you would compute something like this. So this is an example of the capital recovery factor, or the annuity factor. Right? Annuity comes from annual, like anno, I think, is year in Latin. So that's where this comes from. So this means like a yearly thing. Okay, so here's a little bit of a twist on this previous example. So suppose so this is the same example as before. This is, the amount is the same, right? P is 21,061.82, same thing. But here it's saying, suppose you negotiate with the bank and say, can you please defer or delay my first payment? And the bank says, yes, I can do that. So you're still expected to provide a series of equal payments over the same number of years, so over 5 years, except now you don't start from 1, but you start from time period 2. So everything is shifted by 1 time period. The interest rate is the same, right? And so P is the same, I is the same. However, the only difference is this shift. So what happens here? So notice, first of all, that this is not in the standard form, right? For present value. For present value, if you want to compute the present value, it should be 1 time period before the first payment. Now it's not. It's 2 time periods before the first payment. So if I plug in directly, I say I have A, I have I, right? And then I let's say I have, oh, well, you can't say I have, oh, you have N. So you have N, I, and A, right? These are given. So if I choose N equals 5, right? So these are 5 payments. I have I is 6%, and then I have, no, you don't have A. Okay, I'm sorry. Let me erase this part. Okay, so I actually don't have A. I keep mixing that up. Apologies. Oops. So what I was going to say is the following. If I had a way, so let's suppose I'm actually after P given A. Okay, let's suppose I know A. If I compute it, what I'm going to get is a P that is here. Why? Because this P is always 1 time period before the first payment. And then, of course, I would move it back. But of course, in this case, it's a complete opposite. So we're actually asked to find A, we're given P. So what should I do here? So the first question that you should ask is, like, is there a way to convert this into a standard form for the present value? Salman or Khalid?
You can take the present value and move it 1 year forward to year 1.
Yeah, exactly. So if I take this here, if I move it here, I'm going to get some P prime, let's say, right? So I apply interest for 1 time period. And so now this looks like standard form, right? So this starting here looks exactly like a standard form, and then I can just plug in the formula, but instead of using this P, I use this P prime. Okay? So it's kind of similar to the one we saw before, where we had a shift in the time period. There it was for the compound amount factor, but here it's for a different factor, but the principle is exactly the same. If it's not in standard form, can I make it in standard form? What sort of calculations do I need to do to find or to get what I want? And so that's what they do here. They can compute P prime. Again, it's by moving the P. I don't have a graph here, unfortunately. So it's by moving the P 1 time period into the future, applying 6% interest for 1 time period, and I get F given P, and that's my P prime. And then I have a standard form looking series, and so I can just find A or A prime using P prime, right? So this is P prime. Over 5 years with this interest rate, I can find the answer. Okay? So we have 2 more factors, I think, that are left. I think we're going to finish on time, which is great. And we're going to be on schedule. So that means the homework is likely, unless, God forbid, like something goes wrong in the next class, the homework is likely going to be due at the end of the day next Sunday, so a week from today. So a present worth factor is the opposite, which is kind of what I had in mind for some reason before. So you're given A, and you want to find P. And so a question that may be asked for this case is the following. Let's say you want to withdraw $8 every year for a number of years, but you want to put that money in an account right now at time period 0. So how much would you need to invest? How much would you need to set aside now in order to be able to withdraw $8 every year for the next N years, or for the next N time periods? So again, this is the exact opposite of what we just saw, right? What we saw before was A given P. Now we want P given A. What do we need to do? Well, the formula looks very similar, except it's like you guys said before, this part is just the reciprocal. This part is just flipped, because now I need to solve for P instead of solving for A as before, right? So very straightforward. Here's an example of a question like this. So winning the lottery, we saw this in the first example in this chapter. So suppose I want to find basically the equivalent of this lottery payment. So if I give you starting today, notice here that we have an issue, right? We're starting today. So this is not quite standard form, so just be careful. And then I want to give you a payment every year for the next 19 years, right? So the first one is today, and then for the subsequent 19 years, I'm going to give you the same payments. Also today, you're going to get the same value, which is 9.75 million, let's say. The interest rate is 8%, and I want to find the equivalent worth of this payment in today's money, in today's dollars. Okay, so I want to find P. And so notice, of course, you may be wondering, first thing is why they did n equal 19 instead of n equals 20, because if you start from 0, then n equals 20. Well, remember here, if I do, what will happen if I do n equals 20? What is kind of happening? If I just plug in the formula and I use n equals 20, what happens? What happens to my P?
You're subtracting the value from it.
Not sure what you mean. Let me put it this way. So suppose I just blindly say I have 20 payments, right? And I plug in. I will get a P. Where would that P be? Based on like the standard form. In year what, sorry?
Like year -1.
Exactly. So, which is kind of, I mean, weird to think about, but that's exactly what would be happening. In fact, if you do that, so your P, so I'll extend this line, it will be -1, and your P will be here. So this is not going to be the real P, so I'm just going to use a P prime for it, right? And then you would actually need to move that one time period into the future to get your actual P, which you can do. You can still do this, and I think it gives you the same answer, right? So I just want you to see that if you compute P blindly and just use 20 payments, n equals 20, your P is not going to be at time 0, right? Because we always said the P comes one time period before, so that's why it's going to be at time period -1. Okay, so that's just a note. So that's one way you can solve this problem. A nicer way, just erase the pen, is to say, well, this is already in today's dollars. I don't need to do anything with this. I'll just keep it as is. I'll take these guys, which are 19 payments. So now n equals 19. So that's why here we have n equals 19. And that's why I wanted to point this out, right? So n equals 19. I'm going to compute this, and I'm going to get a P that is here at time period 0. And then I can just add this payment to it, the 9.75 that I'm getting at time 0 anyway. And so that's what they do here. So it's 9.75, which is the one at time 0, plus the equivalent worth of the remaining 19 payments, given A, which is 9.75. If I add those up, I get my present value at time 0 for this series of payments. Now, if you do the other approach, which I just described, if you do n equals 20 and you compute it at -1, which is a little bit weird, and move it forward by one time period, you should get the same answer. So I encourage you to verify that. Okay, so this is just a point about being careful about this standard form thing. By the way, the standard form is just what I call it. I don't think it's an official name or anything like that. Okay. So here's an example. Another example. So suppose you're given two savings plans, both at 8%. And so the first savings plan is that, So this is how you're going to save for retirement, let's say. Let's say you're retiring when you're 65 years old. And you're thinking about saving starting from your age, maybe right now, which is 21. And so you're given two options. So one option is you deposit $2,000 every year for 10 years, right? And you start at the end of the first year, okay? After the 10 years, you stop making additional investments. You just let the money that you've already invested just grow, okay? So that's one option. The second option is you actually don't do anything in the first 10 years. But then you start saving $2,000 a year every year until you get to 65. So the amount is kind of the same, but here you're saving it up front. So you're saving it from now, from 22 until 31, I think. Whereas in this case, you're actually not doing the savings now, but you're saving the same amount for a longer number of years, but you're starting much later, right? You're starting the first deposit when you're 32. And so they're asking you to compare these two options and find out which one you should choose. And so here's what they look like. So the first thing that is always nice to do is to plot them, to see what the cash flow diagram looks like, right? And so this is the early savings plan where you deposit $2,000 every year for 10 years, right? So you start at 1, you start at the end of the first year, which was given in the problem. And then after 10 years, you just stop, right? And so you see here, of course, these numbers here, the 0 and the 44, and all of these numbers are, of course, after subtracting 21. So this is relative to today, how many years from now. So that's why it's 44. However, we know if you add 21, it's going to be 65. So that's what your actual age is. Okay, and you're asked to find the future value, right? That's one way we can compute. You can also find the present value if you want. It doesn't matter, because you can go between them, right? You can, if you find the future value, you can go present and vice versa. So one way to solve this problem is to find the equivalent worth in the future of this savings plan. How do we do that? Well, we have the formulas. So again, this is what the graph looks like. I have an equal payment series. So if I wanted to find the future value, notice that if I apply the formula, my future value is going to be exactly at time period n, so it's going to be here. And then I need to move this for all the way to time period 44 by applying interest to it for the difference, right? For 44 minus 10 time periods, 34 time periods. Okay? So similar to before, you just do it in 2 steps. So here's option 1 again. So you apply the formula, right? So you want to find f given a, but my f is actually going to be here. So I'll just write, I mean, you can think about this as f prime if you want, because this is not your final f. You apply the formula, you get this value, but then you need to take this value as I've drawn here and move it all the way to the future. And so how many time periods are you accumulating interest for here? It's 44 minus 10. So 34 time periods, which is here. And then you get your f. So this is for option 1. I need to do a similar thing for option 2. What does option 2 look like? It looks kind of like this. So first 10 years, I do nothing. Year 11, I make my first deposit, and I keep depositing until I get to age 65, which is time period 44. And here, actually, it's easier because my f is going to be here. It's going to be exactly where the blue line actually is. So let me erase the red one so you don't get confused. So I just apply the formula, right? This is more straightforward than the last example. So if I apply the formula, I find that my f is $317,000. So if I compare the two, I see that option 1, investing early, even though it's investing only for 10 years, because of interest, because of compound interest, this amount is going to grow and grow. So I'm better off investing early. Okay, so final thing, I have 3 minutes, so I'll go over this quickly. This is the final case where, if you remember, I told you n goes to infinity. So that's what perpetuity means. It means a series of payments that goes on for an infinite number of time periods. So again, it's a stream of cash flows that just continues forever, right? And this is what it looks like here. Forget this p bit, but see here, you have equal payments going on for n equals, or for n going to infinity number of years. And each payment is for $1,000. Now, of course, as I said before, you may be wondering, like, how come, well, first of all, because n is equal to infinity, or it's going to infinity, you cannot compute a future value. It's a little bit difficult, or at least, well, I'm actually not sure. Scratch that. No, yeah, you can't do that. No, never mind. So you can't do that. So you can't compute f. However, because of interest, and because if you think about it, these payments, because they're for a fixed amount, they're going to be worth less and less and less and less with time. So the worth of each additional payment, like if you think about it, the worth of the payment that you're getting at n equals 5,000 is going to be very close to zero. Well, 50,000, fine. So the worth of the payments of the $1,000 at n equals 50,000, so at year 50,000, is going to be very close to zero. So the worth of these payments just go down with time, right, as n goes to infinity. And that's why we can actually compute a finite present value for this. Like there's some math behind it, I guess. But you can also deduce it from here. So this is the formula for P given A that we had before, right, for a finite n. And so what happens if I take the limit as n goes to infinity? Well, first thing you notice is that this part here is going to tend to 1, right? So I'm just going to draw an arrow here. This part is going to go to 1 because these things go to infinity at roughly the same rate. And so what you're left with is actually just P is equal to A divided by I, which is exactly what you see here. So this is exactly the formula for this case. So if you have an infinite cash stream of equal payments, A, you can just divide by the interest rate to find how much that cash stream is worth in today's dollars. And again, here we kind of see the math that's going on behind it, why we actually have a finite value in this case. And so here's an example, another one of those straightforward examples. So if you have a perpetual, so you see here the word perpetual is key because perpetuities, right? So perpetual meaning ongoing, forever. $1,000 each year. If I is 10%, how much is the perpetuity, right? How much is the series of payments worth today? And we already know from the formula that P is just equal to A divided by I. I is 10%, A is 1,000, and this is what the present worth is. Okay? So actually, we're right on time, which is great. So this concludes this part of this chapter. We have one more part remaining. Hopefully, we finish the whole thing in the next lecture, which talks about gradient series of payments. So series of payments in which payments are increasing or decreasing in a very structured way. We'll see what that structure looks like. And so I'll stick around for questions. I do have office hours. If you don't have any questions, I will see you guys 2 days from now, so on Tuesday.
دكتور الكوز متى؟
So just give me a second.